The final step of downsampling is now to omit the zeros between the samples to obtain the lower sampling rate. So we will call the signal without the zeros as y of m, where the time index m denotes the lower sampling rate as opposed to n, which denotes the higher sampling rate. So when we go back to our Python example of the sinusoid seen before, what we're going to do now is to remove the zeros. So this is what we're doing here using this array indexing. So we're just taking the n equals to 8 multiples of this signal. So we're removing the zeros, we're just keeping the non-zero values, and then we're plotting here. So this is what we have. This is the downsample without the zeros, and we see that before we were plotting 100 samples, but now when we remove the zeros, we are left with 12 samples from n equals to 0 until n equals to 11. And if we take a look at the spectrum without, this is the spectrum without the zeros. So we remove the zeros, we're calling ST, is with the zeros removed, and we have this spectrum here. So there's a magnitude in dB and the normalized frequency, and we see here that now the signal appears at a normalized frequency of 0.455, and this is a factor of 8 higher than before when we had the zeros in it, because now we reduce the sampling rate by 8. Yeah. And how can we explain this? We can explain this because now we have a new Nyquist frequency, which is the 22,050 divided by 8, and our normalized frequency becomes the 400 Hertz we had times pi divided by the Nyquist frequency times 8, and this is 0.455. That means that removing the zero scales or stretches our frequency axis. And as I said before, in our time domain plot we only have 12 samples left, because when we plotted the 100 samples, but now we remove the zeros and we get 12 samples. So this is what's shown here, and this is what's showing here with the new normalized frequency, because we changed the sampling rate by 8. By changing the sampling rate by 8, we also have a new Nyquist frequency, and then we need to this means that removing the zeros scales or stretches our frequency axis, and we need to adapt to calculate the normalized frequency. Yeah? So how are the frequency response of the spectra of y of m and xd of n are connected? So what we can do, we can simply take the Fourier transforms of them. So this was the signal still with zeros in it, so most of the sum here will only contain zeros. So what we do, we only need to let the sum run over the non-zero entries, so it's only on every nth entry. So we replace n by m times n, and we will have from here to here we are replacing n by n times n for all integer n. So now is without the zeros, and we can make the connection to the Fourier transform of y of m by making the index substitution m for n in the sum. So we have this thing here, and this is this result, and it shows that the downsampled version with the removal of the zeros has the same frequency response, but the frequency variable omega is scaled by the factor of n, capital N, which is the downsampling factor. So we can see the difference here was the Fourier transform of the signal with the zeros. Here's the Fourier transform, the signals without the zeros, and we get this factor n that is scaling the capital omega. So for instance, the normalized frequency pi divided by capital N before downsampling becomes pi after removing the zeros. It shows that a small part of the spectrum before downsampling becomes the full usable spectrum after downsampling. So observe that we don't lose any frequency in this way because we had multiple copies of the spectrum in steps of 2 pi divided by n, and the spectrum already has a periodicity of 2 pi divided by capital N. So this means that the spectrum between minus pi divided by n and pi divided by n, for instance, but we could take any period of length 2 pi divided by capital N, contains an unique and full part of the spectrum, because the rest is just the periodic continuation. And we can see in these pictures here. So this is the magnitude spectrum of a signal. These two boxes are symbolizing a passband or of an ideal filter. In this case, it's a high pass. So this is our signal, and we are doing this high pass. So this is what it does after passing through a high pass. And then there's the signal spectrum after the multiplication with the unit pulse train, when you're using n equals to 2. So we're setting every second value to 0, and still the 0 are still in the sequence, and we have a shift and add the signal by multiples of 2 pi divided by 2, which is equal to pi, and in effect we obtain mirrored images of the high frequencies to the low frequencies. So we are assuming we have a real valued signal. So observe that the mirrored spectra and the original spectrum, they don't overlap, and it makes the reconstruction easy. So this is the signal spectrum after downsampling, removing the zeros by n. In this example, n is equal to 2, and can observe the stretching of the spectrum by a factor of 2. So in conclusion, we've seen here that the removing the zeros and downsampling and removing the zeros, it scales or stretches our frequency axis.